Hello everybody, so I'm Justin, so coming from Paris, close to Vienna. And today I will present some recent work that we did on non-smooth optimization for robotics in general. And so this morning I had also a talk on this topic, but why are we still talking about physical simulation in the era of world model? So I will try to give some answers. So this is just a motivation. So currently simulation is a major source of data production for robotics and mostly, for instance, for RL. So this is an example coming from NVIDIA with the extreme paper, where we can have huge numbers and massive numbers of how we use simulators today to generate many samples. And if we look at robotics in general, simulation is ubiquitous for teleoperation, imitation, and policy learning. So this is a fundamental block. And so the question is that if we can accelerate simulation, then we can still improve all these fields. So in fact, I would say today's physical simulators remains efficient world models. So we can divide this world in two parts. So on one side, physics-based simulations, we're using mostly scientific knowledge, which suffer from many limitations that we know, but it's still relevant to use them. So limited complexity, symmetrical gaps, static models. And on the other side, today we have this modern era of data-driven world models, which suffers also from many artifacts like hallucination, data hungry, and physical inconsistency. And there is also a question between CPU-based and GPU-based simulation, but I think both of them are fine still today. If you want to be very fast for model predictive control, CPU-based simulators are still the way to go if you want to do whole body MPC. And on the other side, GPU-based are becoming the standard for generating massive amount of data for RL. And ideally, as a community, what we want to do is to build the ideal simulator, which can be both fast and in a way compatible with massive batch computations. So I will try this part of the talk to first talk about accelerating physical simulation from many perspectives and what does it mean. So if we look at simulation and how we accelerate it, we can see that from an algorithmic perspective, architecture perspective, or parallelism. And so we have many contributions coming, from the 70s and 80s in algorithmic contribution. The seminal work of Orin and Firestone, for instance, are there. So with the linear complexity algorithm like ABA, RNA, we have also sparse contact solvers. We have also optimization techniques like first or second order, proximal algorithm, and complementarity constraint formulations. And of course, if we speak about derivatives, there is analytical derivatives which might be helpful. From the architecture perspective, we have CPU, GPU, TPU if you want. We can also work on memory layout and how we organize data, vectorizations if we want to parallelize the stuff. Computation also can be important, like JIT and code generation, and also differentiable pipeline like PyTorch and TensorFlow if we want. And in terms of parallelism, we have at many aspects we can do parallelism, scene level, solver level, and also at the kinetic tree level. So today I will mostly talk about algorithmic perspective of simulation. So it means that we can leverage the solution that we provide on CPU and GPU if you want. And the idea of our vision in the team, in the Willow team, is that we want to revise physics simulation with modern optimizations for scalability, efficiency, robustness, and differentiability. And the core tool that we use is proximal optimization in general. And I think this is the essential toolbox that we try to handle and to embrace in the team because it's very generic and very powerful. So this is the main idea of that is really that you have a cost function that you want to optimize and you will smooth it with this penalty term. And the penalty term, the appearance of the penalty term will decrease over the iterations. And in fact, if you have a convex problem, you make it strongly convex because of this term, and you can handle also non-smooth problem and so on. This proximal optimization scheme embraces many well-known optimization settings like augmented Lagrangian, acceleration method, and so on. So I think it's a very powerful tool that we try to leverage in the team at many levels, and I will explain it today. So I would say that over the past 4 or 5 years, we have been working a lot on simulation and how we can make it more efficient and more reliable. And in some sense, how do we manage to break the simulation problem, at least for the rigid body cases. So physics simulation, in a nutshell, it's very the integration of differential equations by solving it numerically. We have three main stages. The first one being collision detection. We try to infer the contact point between geometries. Collision resolution. We try to infer contact forces and motion of the object according to that fulfills the physics principles. And then time integrations to integrate numerical system. I will start by collision detection. So collision detection is the idea of finding the contact point between all the objects. And if we have n object in the scene, we have n square queries to do. The complexity goes quadratically. So it means that any progress in better solving collision detections will help simulators. I don't know if you are familiar with this setting, but Gilbert, Judson, and Carpentier algorithm, so called JGK, is the most famous one and which has been used for decades in robotics to do the collision between convex primitives and convex shapes and meshes. And so the idea is that you want to find what we call the witness point, x1 and x2, between the two geometries, and which are the closest one. And if the objects are in contact, they collapse and they are equal. And the idea of JGK algorithm is really not to work in the space of the shapes, but in the Minkowski difference settings, which is this convex object if your objects are initially convex. And the idea is that this problem of optimization problem translates to a minimum point problem, which is not necessarily easier to solve because you need to deal with the Minkowski difference, which is intractable to compute in general. I mean, this is the three people behind this algorithm, very fantastic algorithm, and I think all collision detection library is implementing this work. So the idea that what we have been doing in the team for the PhD of Wimonto is to show that collision detection and JGK is nothing more than a Frank-Wolf algorithm. So Frank-Wolf is very popular in machine learning and a very efficient way to see JGK because JGK at this time was seen from the computational geometry perspective and not necessarily from the optimization perspective. So the idea of Frank-Wolf setting is really to compute, if you have a given function to optimize, the idea of JDK is to compute the support function, support point over the convex set here, SK, and to do interpolation to XK and SK, and to iterate over that, and you will converge towards the optimal solution over the Minkowski difference, which is the closest one to the origin. So this is a very beautiful framework. And what we have been showing is that we can accelerate it using standard techniques of gradient accelerations. So the idea that you have Polyakh-Dujitsky or Nesterov acceleration techniques, which helps you to damp the oscillation phenomena which are traditional for gradient-based optimization methods, and to reduce the computational burden of collision detection and to converge and to divide at most by 2 the number of iterations that you need for converging towards the optimal solution. So this is a new accelerated JGK algorithm. So the idea is that just adding 2 lines here help you to get to go quicker towards the optimal solution. Everything has been implemented in FCL++, or the call library, which is an extension of the original FCL library by Dinesh Manucha and colleagues, which is now more robust, more extended, and more tested. And if you want to have the reference, this is the reference of this paper. And so really, the key of our approach has been to reformulate JGK as an optimization-based framework using Frank-Wolf settings, and then to accelerate it using classic Nesterov Polyakh acceleration scheme. And you just need to change 2 lines of code in your existing implementation of JGK if you want to benefit from this advantage. So it's nothing in terms of implementation. Now I will move towards collision resolution. So collision resolution is also the big part of simulators, in fact. And when you speak about simulation and contact point simulation, you need to handle 3 main laws. The first one is the so-called Signorini condition that tells that the normal forces and normal velocities are both positive, but they are complementary. So they cannot be non-zero at the same time. We have also the Coulomb friction constraint that says that lambda is bounded by the cone, so it means that the tangential forces are bounded by the normal forces. And the third one, which is called the maximum distribution principle by Jean-Jacques Moreau, which tells you that when you start to slide, you start to dissipate energy, which maximizes dissipation in the tangent plane of your contact points. Okay, now these three modes can be encompassed by what we call a non-linear complementarity problem, or this form, where on one side you have a lambda, which belongs to a friction cone, and sigma plus the corrective term, which belongs to the dual of the friction cone. So this term is called the deux-axes term, which is just a shift to write the NCP as a complementarity, as a conic complementarity problem. And you have a relation between the contact velocity, point velocity, and the contact forces. So J is the so-called Delaunay matrix. R is a compliant matrix, which can be also a proximal term, and J is a free velocity of the contact. The first thing that we did during the PhD of Quentin Lelidec here has been to just observe the current state-of-the-art methods for solving contacts in robotics. And we cover all the standard approaches, and we show advantages and drawbacks of all of these formulations. And so the key observation from this analysis has been that modern simulators tend to drastically simplify or relax physics at the price of some physical consistency and accuracy, which can then perturb the learning of control policy if you use LL, for instance. So the first thing that we have been working on has been to work on new methods to properly solve the NCP problem of contact. So the idea is that we will be working with the NCP problem directly, and what we have been showing is that we can use this kind of interleaved problem where you will try to solve for lambda according to which is a conic problem over the contact forces. And you have also sigma, which only depends on lambda as a linear constraint, but sigma is also appearing here in the deux-axes term. So we provide what we call a proximal ADNM techniques and a spectral one. I will try to explain what it means, but the idea that it's a splitting method which is able to properly solve this kind of problem. The idea is that we want to be very robust in terms of problem conditionings and having fast convergence. And what we propose is the spectral rules to update the step size used in IDMM, which depends on the conditioning number of the Delaunay matrix. So the secret sauce behind this stuff has been to use proximal optimizations to try to be able to address purely real contact beyond soft contact modeling. And also using the spectral rule to really be able to account for bad conditioning. So the idea that here you have cubes, gigatons weight cubes, and very microgram cubes. So if you use standard linear update rule of IDMM, you won't be able to converge towards a precise solution. But if you use a spectral solution which depends on the conditioning, you are able to converge towards a very stable solution. So this is the techniques. I won't cover it, but everything is referenced in the original work. Just to say that this has been recently reproduced and integrated by Disney Research in the Camino solvers. And so they acknowledge very strong benefits of our IDMM NCP solver compared to the other solutions. And they did that on a large set of dynamical systems like these ones, and mostly on very complex one with a high number of closed loops. Like 75 links and 67 joints, which is much more than what we have currently on humanoids. And this has been highlighted in this Camino using our solver techniques, has been highlighted during the keynote of Jensen at NVIDIA GTC Congress. Okay, the second key progress has been working on when you solve IDM, when you solve a problem involving contact and contact forces and contact velocities, you need to solve often a linear system, which is paired by the Delaunay matrix plus the compliance matrix. And so what we did is that we have been able to go from a cubic complexity to in practice to a linear complexity for solving this kind of system. So how it works, this is a recent work with Ajay. The idea is that you have to inverse this matrix. You don't want to inverse matrices in general if you work with very large scale systems because it takes too much time and too much memory. And the idea is to work implicitly with that. And the idea that behind this formulation, what you have is you have the duality matrix, J, plus the compliance, physical compliance or artificial compliance. And you can use Woodbury formula to provide an inverse of these terms and being able to solve the linear system that we have been seeing before. So now to solve this problem, you need to inverse this matrix, which is hard to inverse in general, because it's a mass matrix augmented by coupling terms, which couples all the links if you have close loops. And so the question is how to calculate that very efficiently. And the answer is in this paper with Vajay, is to extend the classic ABA settings to loop constraint settings. And the idea that if you remove these constraints here, you recover the classic ABA algorithm. If you add this constraint, it becomes trickier to solve it. We provide augmented algorithm settings to properly exploit these coupling terms and using factor graph to try to better exploit the sparsity induced by the graph of constraints, because as soon as you start to have many contact points, you start to have coupling, and now it's a question of constraint. So everything will be presented tomorrow, and the progress again is to go from a cubic complexity to a linear complexity, which might help simulators to scale for very large scenes. So during this week, Ajay will present that the poster associated to this paper. Okay. Other thought that we had in the team is to go from point contact modeling to surface contact modeling, so what we call contact patch. And when you have contact patch, it behaves much more better. So the idea that if you have a contact point, you have the unique condition that we have seen before. When you start to work with surfaces, it's distribution, positive distribution of pressure field, and positive distribution of contact velocities for all the points belonging to the contact patch. And a nice idea developed by Yann de Montmarin, which is here today, is to prove that we can write it as a nonlinear comparative problem again, of this form, which couples toroidal moments and contact normal forces to angular toroidal angular velocities and normal velocities with a complementarity problem, as a complementarity problem. And this extends the classic conditions, stability conditions that we know in robotics for human robots, which go beyond towards the classic zero moment point conditions over the contact surface. So I invite you to look at the poster session next first. Another question is how to invert the physics. Now that we know how to model ONCP formulation contacts. We recently came to this new frictional contact implicit inverse dynamics formulation. So the idea is that you plug your contact model and your system robot dynamics into as a constraint of QP quadratic programming formulations. So it's no more QP. You want also to have control limits. And what you want is that the objective just encodes task objective or task reward. So everything is detailed here, but the idea that we have been providing two formulations, one which is a splitting ADMM-based formulation, and the other one augmented Lagrangian formulations that properly embrace these settings. And what we have provided is a nice way to really project the system. It's a non-convex problem to project on these constraints in the augmented Lagrangian or ADMM-based formulation. So the key point that we add over that is to have an automatic way to reason and to solve this problem and to create and break contacts via non-convex and non-smooth optimization. And what we leverage is non-convex augmented Lagrangian techniques. And this is the result that we can obtain. So here there is, it's just purely inverse dynamics, so no time horizon, it's just pure reflex, but we are able to generate very, very agile motion on the robots. So this is a promise for the future, I would say, in the sense that we could be able to generate very active motion on the robot if we now have preview on this kind of point. Okay, and so today, I think Pierre has a post there on this topic. I would like maybe to note, I wanted to discuss about differential simulation for robotics. We have been working a lot on this topic. It's still an open problem for us. So it's the idea that we want to differentiate for the whole pipeline of computations, meaning not only differentiating collision resolution, but also collision detection. And also to provide automatic reasoning about creation of and breaking contacts. So just, I won't cover it because for lack of time, but just the idea that the first try that we make, so we have a solution which is able to run very fastly. So if you need more than 100 microseconds to solve the simulation problem stage on the Atlas robot here with many bodies, we have shown that we can get the derivative of this problem for less. And so if you double the price of simulation, you can get both the simulation and the derivatives. And so it's a nice promise also for the future to leverage derivatives for learning and control in general. Okay, so the last topic of today is about, it's still related to non-smooth aspect, but the idea is to work on scaling self-supervised goal condition RL using the framework of survival analysis. So the idea that the goal condition RL is a very popular, increasingly popular settings in robotics. The idea is you go from a policy which is just conditioned by the current state, but now you condition it also respect to the goal objectives that you want to reach. And in fact, we have to optimize a very few informative sparse reward, which says that you have 0 only if you reach the goal and -1 if not. And so you can try to solve this kind of problem using it. And so the idea that it's difficult because at some points you can reach a goal and you have information, otherwise you don't have any information, and it's very hard. And the idea is that the value function that you try to learn from the current state and given goal is a very weak signal, and with here the time to reach the infinite time to reach the goal if you want to reach it. So the key observation is that the return only depends on how long it takes to reach the goal, and this is another perspective on goal condition RL that we developed in the team. And the idea is that we want to reframe goal condition RL as a survival analysis framework. So survival analysis comes with two major functions. On one side, we have the survival function, which can give us the probability that the goal has not been yet reached. And we have the hazard function, which tells us the probability of succeeding now, knowing that we didn't succeed before. And from this perspective, what we can do is that we can recover directly probability distribution over the value of functions, and which is directly related to the survival functions. And we have a link between the survival functions and the hazard function for this formula, which is also very tractable. And so the idea is now what we want to do from the previous perspective is that we just want to learn if we know how to compute this one, we know how to solve the problem. And so the thing that we need to learn this ADA model, H theta of pi, so being a neural network, H being now a neural network, which is conditioned by the current state, action, and goal. And we can use, in fact, likelihood maximization, so just supervised learning. And by taking into account two labels, successful trajectories, like this one, the time that for reaching the goal is belong to then the given algorithm that we have for finding a solution. Or if we don't solve the problem, we also provide some sort of observations, which give us also information that the problem is not solvable in this given H array. And the key advantage of this formulation is that it's properly exploits successful and failed trajectories. It's not it's not a Bellman formulation with all the details that we can encounter with Bellman formulations. It's a natural treatment and a logic treatment of sparse rewards, and we can also predict uncertainty over time to do. So by framing everything using the survival analysis framework, we have been able to really scale SRL beyond what has been used so far, like CRL, contrastive restricted learning, much further. So scaling CRL is a release paper of last year, which was able to solve enlarge the solving of problems, and we go even better. So from 2 to 8 times higher problem performance. So as the planning goes beyond, we have been able also to show that our approach is also scaling with the dimension of the problem, unlike CRL. So if you want to have information about that, I think you can discuss during this week with Frankie, Fabian, and Theo team. Last, to finish also my talk is, to promote also open source in the current world. So for us, open source is a catalyst, and it helps us to maintain knowledge in the team, but also it helps us also to distribute our knowledge towards other teams and for real world applications. And the philosophy that you are trying to follow is more with less, trying to reduce the computational burden of simulation and optimization in general, to be able to run things on edge devices. And the idea that we want to have less code, compute data, and bugs in general. So the most famous framework, already mentioned by Ajay, is Pinocchio. More than 10 years of development, and nowadays it's really a teamwork, and we are providing Pinocchio 4 now with all the frictional solvers that we have been discussing before. We have been working a lot on robot perception, and we want to continue on this aspect. And today there will be people talking about this topic, I think. About optimization, we have been starting working on dedicated solvers for robotics, both for optimization in general, generic optimization like QP solvers and differentiability over QP solvers, and also about nonlinear MPC. And finally, simulation, we have called simple and Pinocchio that you can use and leverage to really be able to build your own simulation pipeline. Now I'm done. So this is the Willow and Sierra team at INRIA Paris. And if you go for Paris, we will be happy to welcome you. Don't hesitate to come visit us. And if you want to join the team, also we are really good. Thank you.